Okay, so in the last video, we focused on position, distance, and displacement. Now we're going to keep going with other kinematic ways of calculating and describing motion. So by the end of this lecture video, we'll learn about average speed and velocity and the difference between those two. We'll learn about instantaneous speed and velocity, average acceleration, and instantaneous acceleration. So we can now describe an object's position, and we have measures for describing its change in position. But how do we describe how quickly something changes its position? When we describe how fast or how slow an object is moving, we're describing its speed or its velocity. And speed and velocity are basically the same thing. They describe the rate of motion. However, there is one big difference between the two. Speed is described by a single number, so just the rate of the distance traveled, whereas velocity, on the other hand, is the rate of displacement. And we know that displacement is a vector quantity, which makes velocity also a vector quantity. And so as we know, with any vector, velocity has a magnitude and a direction associated with it. So speed is scalar, SS, easy to remember, whereas velocity is a vector, VV, can't go wrong. So the average speed of an object is the distance traveled divided by the time that it took to travel that distance. So mathematically, this is what it looks like here. The units for describing speed are a unit of length divided by a unit of time. So you'll usually hear something like meters per second or kilometers per hour. In a car, the speedometer, for example, would read kilometers per hour. This is also a measure of speed, just not usually used when we're talking about human movement. Average speed is an important descriptor of performance in many sports and activities. Can you think of any sports where speed would be the main factor or the main descriptor of the motion? Basically, any race. The winner is the person who can complete that specified distance in the shortest amount of time, also known as the fastest or the greatest speed. So the average speed doesn't tell us much about what went on during the race itself. It doesn't tell us how fast the racer was moving at any specific instant in the race. It doesn't tell us the maximum speed or when the racer was slowing down or speeding up. Average speed for the whole race is just a number indicating that on average, the competitor was moving that fast. And to find out more about a competitor in a race, a coach or an athlete may want to measure more than just the average speed. So let's look at an example from a 100-meter dash at the World Championships in Athletics in Berlin in 2009, because that's the soonest that I can find all these data for. So in this table, we see the elapsed time and the interval time for each 10-meter interval for Usain Bolt over here and Tyson Gay over here. So each row is a 10-meter interval of time, or a distance, I guess. And then this column here and here would be the elapsed time, and this column here and here is the interval time. So if we wanted to compare the average speed of the two sprinters throughout the race, then we'd use the formula that we just learned a few slides ago on slide 5, and we would obtain an average velocity of 10.44 meters for Usain Bolt and 10.3 meters for Tyson Gay. And we obtain that by dividing the total length, by the amount of time that it took. So the elapsed time by the time they got to 100 meters. So this would explain why Usain Bolt won the race, because if you break down this value here, it's saying that Usain Bolt travels at a speed of 10.44 meters per second. So in other words, in 1 second, he travels a farther distance than Tyson Gay. Now, what if we looked at the average speed of only the last 50 meters? So if we only looked at the average speed from meters 50 to 100, then Usain Bolt is still slightly faster than Tyson Gay with an average speed of 12.17 meters per second versus Tyson Gay's speed of 12.02 meters per second. If we wanted now to know which athlete had the top speed, then what we do is calculate the speed of the athletes during each of the intervals recorded in this table. So we would have a speed for each of the rows here. And I did that so it would look like this, right? I'm just adding another column here, which is called the average speed. And essentially, if you take that same formula, you're just dividing the 10-meter distance by the amount of time that it took for that interval. So here we can see that Bolt was faster than Gay over every interval up to the 60 to 80 meter interval, where both the runners reached their top speeds and then they both slowed down afterwards. So by taking more split times during the race, we can determine the runners' average speeds for more intervals and for shorter intervals. And this also gives us a better idea of what each runner's speeds were at specific instants of time during the race. So you can see how having this sort of information would be helpful as a coach or a trainer. Okay, so that was average speed. Now let's move on to instantaneous speed. The speed of an object at a specific instant of time is its instantaneous speed. So the maximum or the top speed of a runner during a 100-meter dash or the maximum speed of Penny Alexiak's freestyle swim would be an example of instantaneous speed. Okay, question for you. Is the speedometer in your car a measure of instantaneous speed or average speed? Pause the video and think about that for a second. The speedometer in your car is actually a measure of instantaneous speed. It measures how fast you're going at the instant in time that you're looking at that speedometer. So we can think of instantaneous speed as the distance traveled divided by the time that it took to travel that distance if the time interval used in that measurement is very, very small. So it's the same calculation, it's just that your time is super small. Okay, so far we've learned that speed is an indicator of the rate of motion, describing a distance over time. Now let's talk about velocity. So the average velocity is the displacement of an object divided by the time that it took for that displacement. And because displacement is a vector described by a number and a direction, then average velocity is also a vector that's also described by a number or magnitude and a direction. So mathematically, it's described like this. Velocity is equal to displacement over time. And the units for describing velocity are the same as those for describing speed. It's a unit of length divided by a unit of time. So just like we were able to resolve displacement into its x and y components, we can do the same with velocity. So if we bring back that super fancy football example from the last video, and if you don't know what I'm talking about, you should go watch the last video. The player's displacement from the instant that he received the ball until the instant that he was tackled or stopped the play was minus 10 yards in the x direction and plus 30 yards in the y direction. And his resultant displacement was 31.6 yards down and across the field. So if this kick return lasted 6 seconds, then we can calculate his average velocity. And this is what the calculation would look like. So on the left-hand side, we have the average resultant velocity of the displacement. So this is what we measured here, the 31.6 yards as the displacement over the interval of time that that displacement occurred, which was 6 seconds. So if we divided that displacement by the amount of time, then we would get a velocity of 5.3 yards per second in the direction of the resultant. So if we wanted to then split that velocity into its x and y components, then we can apply the same velocity equation to the displacement in each of the directions separately, basically. So the displacement in x divided by the same amount of time, and then the displacement in y divided by the same amount of time. And you get a displacement in the x direction of negative 1.7 yards per second, and a displacement in the y direction of 5.0 yards per second. Oh, shoot. So this is what the calculations would look like. On the left-hand side here, we have the average resultant velocity. So this is the average velocity of the displacement that we measured, which was 31.6 yards. And if we divide that by the 6 seconds that it took for that displacement, then the average velocity of the runner would be 5.3 yards per second in the direction of the resultant. Now, we could also split that velocity into its x and y components by simply applying that same velocity equation just to the displacement in the x direction and in the y direction separately. And we end up with average velocities in each of those directions. So in the x direction, we have an average velocity of minus 1.7 yards per second. So remember that the minus is the direction. So that's saying 1.7 yards per second towards the origin, right? And then in the y direction, we have a velocity of 5.0 yards per second. So just as with displacement, the resultant average velocity is larger than any of its components. And that is a sanity check for you. You should always make sure that that's the case because the resultant is always the hypotenuse. Okay, so just as with displacement, the square of the resultant average velocity should equal the sum of the squares of its components. And that's just the Pythagorean theorem. So this would be your resultant velocity vector. And then that is always equal to the square of your x and y components. And so here I've written out the math to make sure. And sure enough, this matches the resultant average velocity of 5.3 yards per second that we calculated on the previous slide. Thank goodness. Okay, so in the 100-meter sprint, both speed and velocity would be good descriptors because the race is just in a straight line. The runner's speed and the magnitude of the velocity towards the finish line would be the same. However, if we think of an activity in which the direction of the motion changes, then speed and velocity are no longer the same. And one way to know whether to use speed or velocity is to think of the motion that you're analyzing. So if that motion is in a straight line and it's rectilinear, then you can use speed. If, on the other hand, the direction of the motion changes, then you need to use velocity because you need to add in that component of direction that's going to factor in the motion changing directions. So if you think of a 100-meter swimming race in a 50-meter pool. So here's the pool. It's 50 meters long, but we're talking about a 100-meter swimming race here. If the first place finisher completes the race in 50 seconds, then we can calculate the average speed, which is the distance traveled divided by the time. So we calculate 100 meters divided by 50 seconds, and that's an average speed of 2 meters per second. Now, what about velocity? The equation for velocity is displacement over time. And if the pool is 50 meters, then the swimmer actually ends the race where they began, making their displacement 0. So the average velocity would also be 0 because you're dividing 0 by 50 seconds. In this case, average velocity and average speed are not the same, and the average speed would be a better descriptor of the performance during the race, right? It's just a rectilinear motion, straight line, speed is the way to go. Okay, the only thing we haven't discussed yet is instantaneous velocity. So it's really similar to the concept of instantaneous speed, except that you're also including a direction here. If we measured average velocities over shorter and shorter and shorter periods of time, then practically speaking, we'd eventually have a measure of instantaneous velocity. And when we speak of the magnitude or the number of that resultant instantaneous velocity, the number is the same as the instantaneous speed of the object. But a resultant instantaneous velocity can also be resolved into its components in the directions of interest. So for the football player, we could describe his instantaneous resultant velocity, and we could also describe his instantaneous velocity in the x direction, so across the field, or in the y direction, which would be down the length of the field. And if we were concerned about how quickly he was gaining yardage, then his instantaneous velocity down the field in the y direction would be important. So here's a graph showing a calculation of ankle displacement over time. So another way to say that is velocity of the ankle, right? So we have displacement along the y-axis and time along the x-axis. So if you were to calculate the velocity from time 0.02 to time 0.1, that would be an average velocity. However, each step on the graph here shows a different velocity calculation. So the change in time for each of these steps here is 0.02 seconds, which is really close to instantaneous. So basically, what you can get from this is that as delta t approaches 0 seconds, the average velocity approaches the instantaneous velocity. In downhill skiing, which velocity do you think would be more important, average or instantaneous? It's not so much the instantaneous resultant velocity that it's important. It's the component of this velocity in the direction down the hill that will have the greater effect on the results of the race. Okay, so we now have a pretty large repertoire of motion descriptors. We have position, distance traveled, displacement, speed, velocity, and we can also use components of displacement and velocity to describe an object's motion. And when I talk about components, I mean the x and y components. So if I throw this ball up in the air and let it fall back down, and this is me throwing a ball up in the air and letting it fall back down, how would you describe this motion? So you might say that the ball moves upwards and then it slows down on the way up and then it begins moving downwards and it speeds up on the way down. Another way to describe how the ball slows down or speeds up would be to say that it decelerates on the way up and it accelerates on the way down. So mechanically speaking, acceleration is defined as the rate of change in velocity. And because velocity is a vector, acceleration is also a vector with a number and a direction associated with it. So when an object speeds up, slows down, starts, stops, or changes directions, it is accelerating. So average acceleration is defined as the change in velocity divided by the time that it took for that velocity change to take place. So it looks like this mathematically. And from this mathematical definition of average acceleration, it's apparent that acceleration can be positive or negative. If that final velocity is less than the initial velocity, then the change in velocity is a negative number, and so the resulting average acceleration is negative. And this happens if an object is slowing down in the positive direction. A negative average acceleration will also happen if the initial and final velocities are both negative, and if the final velocity is larger than the initial velocity. So this would occur if an object is speeding up in the negative direction. The units for describing acceleration are a unit of length divided by a unit of time for velocity, and then that's divided by another unit of time. So the standard imperial units for describing acceleration are meters per second or meters per second squared. So if a car ad says that the car can accelerate from 0 to 10 meters per second in 7 seconds, what is its acceleration? Based on the mathematical formula that I just showed you in the slide before. So it's a change in velocity over a change in time. And we know that its initial velocity is 0 and its final velocity is 10 meters per second. So we're plugging that in here and dividing it by the amount of time that it took for that change in velocity. And we get an average acceleration of 1.429 meters per second squared. So what does that number actually mean? It means that for every second that the car is driving, it's increasing its speed by 1.429 meters per second. So if the car is already moving at 5 meters per second, for example, then after 1 second, its speed would increase to 6.429 meters per second because we're just adding this number to the existing velocity of 5 meters per second. So if we measured average acceleration over shorter and shorter time intervals, then we'd soon have a measure of instantaneous acceleration. And instantaneous acceleration is that acceleration of an object at an instant in time. It indicates the rate of change of velocity at a specific moment in time. Because acceleration is a vector, it can also be resolved into its x and y component accelerations. And this is true for both the average and the instantaneous accelerations. And the difficulty in understanding acceleration is that it's not directly observed like displacement and velocity are, because the direction of motion is not necessarily the same as the direction of the acceleration. So let's pretend we're walking around a room and we're facing the north wall or the top of the slide here. So I've drawn out my coordinate system here to define my origin and what the positive and negative directions are. So in this case, the y direction is the sort of north-south direction, and north is positive, and the x direction is this east-west direction with east being positive. Okay, so for the sake of this example, we're only concerned about the north-south direction. So according to my coordinate system, motion towards the north is positive. So as you begin walking forward or towards the north wall, your velocity towards the north is positive. And since you speed up in that northerly direction, then your acceleration is also positive. Now, when you slow down and stop, your velocity north decreases to 0, and your acceleration has to be negative since you're slowing down in this positive direction upwards. So this can also be described as acceleration in the south direction. So as you start walking backwards, you speed up towards the south wall. Your velocity is now negative and increasing because you're moving in this negative direction downwards. And your acceleration is also negative because you're accelerating, you're changing your velocity in this negative direction. So let's try to make things a little bit clearer about acceleration here. If you're speeding up, your acceleration is in the direction of your motion. If you're slowing down, your acceleration has to be in the opposite direction of your motion. Okay, so maybe just read those two sentences again and again until they make sense to you. If your velocity is increasing, if you're speeding up, then automatically or naturally your acceleration is in the same direction as your motion. Whereas if you're slowing down, if your velocity is decreasing, then your acceleration is in the opposite direction. Okay, that was a lot of information. Sorry for the long video, but we learned a lot of things. We learned about average speed and velocity, the difference between the two. We learned about instantaneous and average velocity and instantaneous and average acceleration. Please stay tuned for one more video on linear kinematics.